Hello, I believe we are live. Hi, my name is Valerie Mikles. Welcome to Virtual Balticon 54. This is a panel for weather satellites saving the world from low Earth orbit. And again, my name is Valerie. I'm an author and I work on weather satellites for NOAA with the JPSS program. And I'm going to share my screen. Let's see. Share that and then present that. So just a few disclaimers to start with. The views expressed herein are mine and do not necessarily reflect the views of the Department of Commerce, NOAA, or any of its sub-agencies. And they also do not reflect the views of Science and Technology Corporation, for whom I am a contractor. This is very weird not being able to see everybody's faces. But a little bit about me as a scientist. In second grade, the teacher informed us that astronomy was no longer a part of the science curriculum. Naturally, I became obsessed with astronomy. In 11th grade, I was part of a National Science Foundation summer program, and I was quizzing one of the TAs about black holes, and he recommended a book called Black Holes and Time Warps. And the stories in the books, it had some incidental stories about grad school, and I thought, that sounds like a really cool place. Maybe I should go. And so I did. I got my PhD in astronomy in 2008, and I hunted black holes for a while. And then in 2012, I used all my knowledge about satellite detectors to start working for NOAA. And this is my artist conception of a black hole. Since I didn't know what the black hole looked like, I just used this, and he's eating his neighbor star. And I hope you can see my arrow, but otherwise, here we go. So other things I do, this is my beanie thing. He's a beanie thing, and it also spells be anything. I'm a science fiction author. I write hard sci-fi and queer sci-fi. My newest book is called The Chinali Virus, and it's a great time to release a book in the middle of a pandemic with the name virus in the title. I'm also a screenwriter and producer. I have a whole series of films about asexuality and asexuals trying to survive in a hypersexual world. And I'm also learning ukulele and a guitar, and sometimes I record myself playing songs. And you can find out more about me and all the random stuff I do at valeriebean.com. And just a note, if you have a question, please put it in the Q&A. When I'm in share screen mode, I can kind of see that you have questions, but it's hard for me to read them without stopping my whole presentation. So I will definitely get to them at the end. But let's talk about the weather. So what's the weather? It's the first question you ask every day. It's not, will it rain today, but when will it rain? Where will it rain? How long is it going to rain? How hard is it going to rain? And this is not a simple question to answer. We need global data to look at our local forecasts. Weather is driven by broad scale patterns in the atmosphere and jet streams and weather fronts. Hemispheric and global information is required to get the accuracy of forecasts we enjoy today. And localized topography can have a significant impact, like if you're next to a lake or next to a mountain, it will all start to make a difference. And the wrong forecast can have very big economic repercussions for travel, commerce, agriculture, manufacturing, whether you fill roads with potholes, whether you've knocked over a crane for building houses. I mean, all of that stuff relies on weather forecasts. So how do we get global information? Well, in the 1850s, that was our first big advancement, was the telegraph. And we could actually share information about weather conditions over a distance. We could actually get ahead of the weather instead of just being in the weather. In the 1940s, we had the modern computer come in, and that allowed for numerical weather forecasting to replace hand calculations. So we could do more complex calculations at a higher speed. In 1960, TIROS was the first polar operational environmental satellite. TIROS just had a birthday in April, and you can look up stories about TIROS-1. It was slightly taller than a man, but it was a polar satellite, and it got global data for local forecasts. In 1975, we added our first geostationary satellite, and geostationary comes later because they're in higher orbit and it's a little harder to get out there. So the first weather satellite, this is TIROS. It was launched April 1st, 1960, and it took snapshots of clouds every 10 seconds, and it sent back almost 20,000 usable pictures that were used for operational weather forecasts. That means, you know, within hours of getting the data, it was in the hands of a forecaster. It died after 77 days due to electrical failure. Its mission life was apparently only 100 days, so it did make it most of the way there. One of the cool things is it took a picture of a tropical cyclone over the South Pacific when it was only 9 days old. And that's TIROS. So since then, we've launched a lot of stuff, and there are almost 5,000 objects currently in orbit, and the vast majority of these are space junk. They no longer function. These numbers vary based on where you Google and when you Google and what size objects they're counting. If you get it down to satellites, it's about half that. And we launch 300 to 400 new satellites per year. I mean, some of you have heard about Starlink. They're launching the whole fleet of satellites. Just under 700 of these are used for Earth observation, and not all of those are for weather forecasts, but I put a link at the bottom to UNUSA, the United Nations Office of Outer Space Affairs, and they have a space object register, and so you can see what's up there and what's operational. So there are two types of weather satellites that we go with. There's the geostationary and the polar. In terms of weather satellite, you have your geostationary orbit, which is in high Earth orbit. You get a concentrated view of a single region of the Earth. So it would be like only over this half of the US or only over this half of Europe. These are very good for short range forecasts because they're looking at changes over a single area in a short amount of time. Then you have your polar satellites, which are in low Earth orbit, and these orbit about 14 times a day. So you get a view of the entire globe, but there are certain places where you're only going to get two snapshots per day. So that's not very good for short term when the weather is changing in minutes and hours timescales, but it is still very good. It's better for longer range forecasts in the 3 to 7 day range. Then you have your space weather satellites that typically sit at a Lagrange point. So they get the full disk view of the Earth. They can predict solar wind impacts, and they have their own special thing. Okay, how long do modern satellites last? We'll answer this live. So your modern satellite might last, the mission time is 5 years, but they last as long as they have fuel and are functioning, and we try to make them last as long as possible. So I think I come back to that later, so I will. So this is a picture of the NOAA operated satellites. So these are just the ones operated by NOAA and NOAA NASA agencies. And those two are mine. They're in a polar orbit. There's SNPP and NOAA 20, which used to be JPSS-1. So if you see anything that's JPSS, that's now NOAA 20. So JPSS is a Joint Polar Satellite System. It refers to polar orbiting satellites. You have SNPP, which was launched in 2011. It was on a 5-year mission. JPSS-1 kind of got delayed, so then it was pressed into operations in 2014 when it was supposed to be about dead, and we're still using it, and we expect to use it probably. We don't see it failing anytime soon. As long as it doesn't have a catastrophic failure, we're still searching for ways to keep using that data for as long as possible. But I believe we do have to deorbit it maybe in 2030, 2040 range, because at that point it won't have enough fuel for us to keep it in orbit. But in terms of how long they last, we do like to keep them up as long as possible and as long as they're working, because we like the continuity of information. You have NOAA 20, which is JPSS-1, which was launched in 2017. It became the primary satellite for weather in 2018. NPP and J1 are on opposite sides of the Earth. So So they kind of complement each other in terms of when they pass over things. Then we have J2, 3, and 4. These are already being built and getting checked out. The notion was that all of the satellites would have the same instruments by the same manufacturers and essentially be comparable. The J2 launch is scheduled for 2022, then J3 in 2027, and J4 in 2032. These are all subject to change and subject to whether the previous satellite is still working. So, our new satellites have these wonderful advanced instruments, and I rearranged all these slides like 2 days ago. It's very fun to see what I did. But if you look at TIROS-1, which was the first weather satellite in 1960, it had 2 instruments. It had a wide angle, low resolution camera and a narrow angle, high resolution camera, and it only looked at visible light. It was only taking pictures. The JPSS has 5 instruments. It has the visible infrared imager, an infrared sounder, a microwave sounder, an ultraviolet spectrometer, and an infrared radiometer. So we're going over significantly more wavelengths, and we have, well, we have more advanced technology in our imagers, so we have better resolution. So here's a little bit more about the instruments, because I hear people like instruments. The CRIS instrument, as I said, was infrared. Its resolution footprint is about 14 kilometers. It works with the ATMS, which is microwave sounder, as a footprint of about 35 kilometers. And together, these two create temperature profiles, sounding profiles that improve the 5 to 7 day forecast significantly. Then you have your VIIRS, which is your more typical visible camera, and it also has infrared channels. It has moderate resolution bands, which are 750 meters, but it can take high resolution images at 350 meter footprints as well. And this is very critical for imagery and snow and fog and clouds and smoke and vegetation and basically anything that we can see. Then we have the OMPS instrument, which is an ultraviolet instrument. It was built to monitor the ozone and is very sensitive to that. And then we have the series, which is an infrared radiometer, and it studies the radiation budget, which is essentially how much energy is coming in and how much energy is going out of the atmosphere. And that's more of a climate focused type of instrument information, but also very important. And I have a picture below of a naked satellite with all the instruments attached to it, and a person who's apparently holding it up with the strength of the force. The JPSS-1 instrument was built, or it was assembled at Ball Aerospace in Colorado. So imagery is important, but there's a lot more we can do. So before we launch a satellite with all the instruments attached, we subject it to very harsh conditions to make sure that it doesn't fall apart on the way up to space, because the rocket is not a luxurious and smooth ride. So there's vibration and acoustic testing that simulates a launch. Then we do EM testing that simulates solar flares so that we can tell if something's going to break. We do thermal vacuum, which simulates a space environment. We put it into a vacuum. We chill it down to cold temperatures because there is no room temperature in low Earth orbit. And then we also test for just compatibility with the information. Can it send signals to our ground system? Can our ground system read it and run end-to-end testing to make sure that the moment it gets up there, there's not going to be this huge stop in data. And if an instrument fails the test, it can delay the whole launch. And so, but the testing is important, because if it fails a test, you can say, this is very important, we need to fix it. Or you say, this is something we can live with as long as we characterize and understand how broken it is. So when you launch it into space, it goes in a rocket. And this is a Delta II rocket that the JPSS-1 was launched on in November 18th. And then this little dot here is the launch pad where J1 was launched. And the SNPP satellite, its predecessor, was flying over, and it took that picture with its day-night band. So I just love that picture, that it can see, you know, its follower. It's like, hi, you're getting ready to launch, come join me. Yeah. Let's see, this has a play button. So SNPP and J1, which is now N20, are separated by half an orbit, so one comes around and the other. The JPSS-2 instrument will launch on an Atlas V rocket, for those that are rocket fiends, and it will be inserted in between the two at a quarter orbit, and after which we will put N20 and J2 in opposite orbits, and then, so there's going to be this complicated ballet of trying to get J1 to its new orbit. And so we've done a lot of scenarios that evaluate the way we're going to reposition it, because every ounce of fuel has to be accounted for, because we want to maintain control of the satellite. That's not what I wanted to do. So once your satellite is in space, it has to get the information to the ground. And as I said, the satellite orbits every 100 minutes about 14 times a day. It's at an altitude of 824 kilometers. So when it's flying over the ground station, it's going very fast, and it has to send down many terabytes of data in only a few minutes. So we have ground stations at Svalbard and McMurdo are our main ones, and we have backup stations at Fairbanks or Troll if there's a conflict, like two satellites flying over trying to use the same ground station. We can move to a backup, or we save the data on the satellite for half an orbit. But we don't like to do that. We're trying to deconflict as much as possible. Once it gets to the ground station, the data will move to an operations center. There's also information from the operations center that can tell the satellite to move one way or the other if it needs to do a maneuver. And then it goes to data processing. From the time the satellite takes the picture to the time it reaches the weather forecaster, the maximum time that takes is 90 minutes. And 50 minutes of that is coming from just being the oldest data in the orbit. So it moves very quickly. N20 produces about 4.5 terabytes of data per day, and NOAA has archived almost 20 petabytes of data from assorted NOAA missions, and I wrote that fact several years ago, so there's probably a few more petabytes in there by now. So what data are we processing? Every satellite weather forecast starts as a photon on a detector. And well, they don't all use CCDs, but the general notion of a CCD is the light hits a detector, the detector, pops off an electron, and then we count all the electrons in that bin, and that's how we know how bright it is. And so our raw data records that we get from the satellite have the number of counts and the location on the pixel location, and some of them have the energy wavelength information. The next thing that happens is we process that with some geolocation information to add it. We use instrument calibrations, which tells us this pixel is more sensitive to light than that pixel. So when you're doing that, that's how you balance these radiances or brightness temperatures. We add flags for if it's day or night, or if there's sun glint on it, because we want it to be as obvious as possible whether the data on a given pixel is worth putting into a forecast, because it has to happen very fast in a very automated way. So once we have this, we have a sensor data record. This is not a picture, but it has the calibrated raw information, so you can easily combine and compare different records. To get the environmental data out of this, each instrument has multiple channels that are sensitive to very specific wavelengths. And so we chose these channels specifically so they could detect certain energy signatures either alone or in tandem. So in this picture here, if you're looking at a forest, it's going to be very faint and invisible and somewhat brighter in the near infrared. But if you're looking at snow, it's going to be brighter invisible and brighter infrared. So if you look at the difference here to here versus here to here, you can tell what you're looking at. And the more information you have, the more points you have on this curve, the closer you can get to decoding exactly which of these curves you're on. Differentiating clouds and snow is notoriously difficult, so we try to always have bands available to do that. But in general, you can tell whether you're looking at fire, vegetation, or snow by understanding how your channels play together. So more than pictures. So we're not just taking pictures of clouds. We are looking at clouds like where they are, what are they doing, how high are they. For aerosols, we want to know, is there air pollution? Is there smoke? Is there volcanic ash? Is there snow? Is there ice? What's frozen? How long has it been frozen? For the oceans, where are the currents? What's growing in the water? Is there a lot of algae or sediment? For land, what kind of dirt is it? Is there anything living on it? Is it healthy? We also look at rainfall and soil moisture, and rainfall predictions are very helpful to prepare for flooding disasters. Wind direction, wind speed, temperature, water vapor profiles, ozone. We have lots of data products that we create for NOAA for our users, and then we have users that just take the raw data and then go calculate the information that they need directly. So there's a lot that you can do with the weather data. So as I said, we have it from an operational control center, it goes through a data processing center, and then we send it out to our users, who are usually weather forecasters, but sometimes other people. Every data product that we create operationally, like in that 90-minute time frame, has to have a user that says, I need this in real time or I can't do my job. And when they get that, they give us some feedback. So maybe they have a buoy in the ocean that's also taking data, so they can tell us, hey, your satellite doesn't match our ground truth data, and then we can make adjustments in the science. There's additional science development. Then once the science is mature, they can go into a research to operations kind of transition. Then we integrate the new operational algorithms into our system and test it, and then that becomes the new operational product. And it takes a lot of people. So if you're out there and you're not quite a scientist, but you love programming and working with scientists, there's always going to be work for you with us. You have to speak Fortran, but maybe Python will work. So who is using satellite data? Who are these users? As I said, the National Weather Service is one of the big ones because they provide the forecasts and warnings. We also have National Centers for Environmental Prediction, and I've only listed a handful here, but there's more than this. But aviation weather, they tell you about hazardous flight conditions. Hurricane and storm prediction, which is probably one most people are familiar with. We have ocean weather, so if you're at sea, you need a different forecast than if you're on the land. And space weather to tell us if there's a solar storm, if we should shut down something. We also have the National Marine Fisheries Service, which is another branch of NOAA, but they are users of weather data. We have the Environmental Protection Agency, the Department of Agriculture, U.S. Forest Service, so they want to protect their forests and monitor fires. Department of Defense also takes all our data, but they don't tell us why. That's on them. So now that I've told you how we get data to the users, let's go save the world. And as a disclaimer to this, I don't do this science. I help the people who do the science make sure they can get to continue to do the science. But I love their science. So, as I said, National Hurricane Center, big one in terms of weather advisories and hurricane advisories. I don't know if any of you heard earlier this week, or was it last week? Tropical Storm Arthur came across the coast of the Carolinas. This is the 6th year in a row our hurricane season has started early, and they issue these warnings, and they put this yellow part here where there's going to be tropical storm information. And what's really cool is if you go to the National Hurricane Center now, they have all these animations for all of this stuff. I'm still a still frame kind of person. Okay. So in this one, the hurricane watch has become a warning, and the difference is that the conditions are going to happen, they're expected to happen, as opposed to they're possible. And then you get here where Arthur just went off the coast and did its own thing. So the National Hurricane Center no longer had to produce any new forecast because it's like, here it is. But the NSEP, the ocean, the sea weather people, they're probably still taking a look at this for anybody who's crossing the ocean. I cannot see my types. So in terms of forecasting, we've actually gotten way better at predicting where our hurricane path was in a 1970 versus today. So if you look at the 72 hour forecast, in 1970, you could predict where it would make landfall 72 hours in advance within about 250 nautical miles, or 450 if you go by this square foot. But today that number is down, you can get it to with 150 nautical miles. And this makes a huge difference in terms of what zones you evacuate, what construction equipment has to be put away. And so it can save a lot of money the more you can reduce that error bar of where it's going to make landfall. And the other cool thing that this plot shows is that we've added a 96-hour forecast and a 120-hour forecast, which there was absolutely no point in doing in 1970 because the error was just too great. So, so the better prepared we are for evacuation, the more we can save money. We can do this because we have significantly better resolution in our instruments. We can actually see where the center eyewall is now from a satellite, whereas before we were kind of going by land-based data and airplanes flying into it. So we have higher resolution, better sensitivity, and better processing, and all of this feeds into having more accurate forecasts. This is a picture with the ATMS instrument on this side compared with its predecessor, which was named AMSU, which flew on NOAA 15 through NOAA 19. This used to be the most advanced instrument out there. And you can see with the older instrument, you have all these gaps in the passes because, you know, the camera was taking good information, but it wasn't passing close enough. So now we have these wider swaths so that we can fill in those gaps and actually see what the center eyewall is doing. So we have higher resolution, wider swaths, smaller gaps between passes. And so we not only can we better predict the path of the hurricane, we have more information than we ever did before. So we have new science coming out to better understand how the eyewall structure works. And so that's really cool. So this is Tropical Cyclone Amphen, which also happened last week. It was super cyclone, equivalent to a Category 5 when it hit India and Bengali. And it's kind of tragic. So it hit India and Bangladesh, and so far more than 80 people have been reported killed. There's a huge problem trying to measure disaster relief with the COVID crisis versus the cyclone crisis, because I don't know if any of you have ever been in a hurricane shelter, but it's not ideal for keeping distance. And then when anybody needs medical attention, medical support, there's a balance there because you don't want to save them from one thing only to have them die from something else. So from the NOAA side, data sharing becomes very important to this. There's an international charter that allows our US Joint Typhoon Warning Center to share information with weather forecasters in New Delhi. So the people that are there, so we're not withholding information that we know can save lives. And this international data sharing is actually very important in terms of the global community because weather doesn't understand borders. So this is Hurricane Dorian. This is a Category 5 that hit last year. This data product is rain rates. It's actually combined from 12 polar satellites and 5 geostationary satellites. So when we're looking at this, we are actually, in our forecast, there are certain algorithms that we try to get as much information from as many satellites as possible. And sure, maybe one is weighted more than the other, but more information tells us more information. So in the case of this one, we had some accumulated precipitation, I believe this is still Dorian, of nearly 2 feet of rainfall over the Bahamas, and this was the accumulated precipitation. And so then we had these flood maps that we were able to send out and say, this is where the flooding is worse, this is where you need to concentrate your rescue, this is where there's still dry land that you can actually send people to. So NOAA is very big on their flood maps. So another situation outside of hurricanes is fires. And some of you might have remember from back in January when Australia was on fire. It actually started way earlier than that, and still parts of it are on fire. But in terms of fire containment, when we're flying over, we see where the fires are. So we're worried about fire containment, air quality measurement, and knowing where the fire is definitely going to save lives. These are some images from the NPP satellite, this is the day-night band, which is when with the VIIRS instrument, it can detect just light at any wavelength. What's shining? Is it electricity? Is it reflected moonlight off of airplanes? And then we can see where the fires are and where they're spreading and where those burn areas are. And then we have a fire product. Well, no, wait, this is infrared of where the fire border is. So one of the fun things, well, not fun things, but one of the vital things that we do with our tracking of the fires is figuring out, I can't see all my words. So we use our VIIRS real-time imagery to aid any fire service with the location and the spread of the fire perimeter. And this is a Swan Lake fire. And this here is our fire product over here, showing where we have some burn lands. One of the things that comes out of fire is smoke and dust, and some fires are on purpose. There were some purposeful seasonal fires in Mexico that they used to control farmland and woodland. And we could see the aerosol smoke and dust tracks. It's one of the things we track because then we could tell if smoke is coming our way, if dust is coming our way, if it's going to affect air quality warnings for that day. And there's this thing called the J-Star Mapper. If you go to Google and you type J-Star Mapper, then you can find this, and then you could enter the satellite. This is for NPP or NOAA 20, and you could pick your data products and you pick your date, and then you can play with the data in real time, or maybe within an hour of real time. Another cool thing that we do is track the vegetation health. And the vegetation health is a series of vegetation index and brightness temperatures, and it's combined to tell us where the land is healthy, that's the blue parts, where it's in distress, that's kind of the red parts, and where it's in the middle. And this kind of information really helps farmers tell when to plant their land. It helps us predict drought. In previous satellites, we did this with a 16-kilometer resolution, and then we got it down to 4 kilometers. With JPSS and VIIRS instrument, we can get this down to 1 kilometer resolution. So we're getting closer and closer to the size of an individual farm. But as I said, this kind of thing helps us track the drought, so we can actually see the stress on the land getting worse so that we know a drought might be coming. And then when the drought gets there, we can actually see the spots on the land where it starts to get healthy before the drought ends. So even though the drought is severe, we can see that the land is healing, and we can predict the end of the drought as well. And with drought, it's always very important to mitigate starvation and death with your drought monitor. So this is another map of the vegetation health. One of the things that we've learned with vegetation health is if you have very healthy land and a lot of rainfall in certain parts of Africa, it is good for mosquitoes as well. And this could indicate a risk of malaria in the area. And if you can predict an outbreak of malaria, which they believe they can do within 1 to 2 months of it happening, this allows health organizations to mobilize. We can move medicine and supplies in that direction, and then we can mitigate the disaster that would be related to this disease for which we have a vaccine. So I have no idea how fast I've been talking, and I don't see a clock on my screen, but some final thoughts. Satellites have greatly improved our weather forecastability. If we have accurate forecasts, we can save lives, and with some international cooperation, we can also save some more lives, and we just want to save the world. And I want to thank you all for being here. And I want to point out these wonderful Twitter handles. If you are on Twitter, you can follow JPSS program, NOAA Satellites. Both of them love posting stories. There's also a place called SIMS and the NASA Visualization Lab, and some of my shares came from their blogs, from their shares. And then you can also find me on Twitter. I'm Valerie Bean. And I believe I will now take questions. Oh, time is only 5:34. Can you talk about some foreign satellites we use? Sure. Start my video. Okay. Stop share. Start my video. Can you see me now? Okay, so some of the foreign satellites we definitely use the EUMETSAT MEDOP satellites. That's one of the big ones that we use. Sometimes we share information between the satellites, or not between satellites, we share instruments. So you'll have the same instrument on an American satellite and then on a European satellite. And that really helps us with the cross correlation of the satellites. In terms of the data, we often have data share information. So we either will agree to use their final data product without seeing their raw data, or we could ask for their raw data and then send it through our own algorithms. And that is determined by individual negotiations. But a lot of times scientists like to use their own algorithms. With JAXA, we also coordinate with JAXA. We have a GCOM W1 satellite in the JPSS, as part of JPSS program. And so we have an arrangement with JAXA to get their data, but there's very firm limits on who can see the raw code or who can't see the raw code and what computer it can be on. So there are certain things that are on lockdown that have to be processed in certain ways. But we definitely do want to make use of foreign satellite data. And there's a World Meteorological Organization where scientists from all over the world get together and decide these are the essential data products that we need to look at. This is how big the pixels need to be. This is a sensitivity that we would like for that. And so then that information then feeds into the individual programs so that we know how to best design new instruments to meet the need of the science community. Okay. Is there a role for LEO satellites? There is always a role for LEO satellites. So JPSS is a LEO satellite. It's low Earth orbit, and it's polar orbit. So LEO is LEO and polar orbit are very similar and overlapping in terms of our use of weather satellites. We kind of use them interchangeably with JPSS. And yeah, the role of the satellites is to get the full globe data, the full global information from a single instrument. And that's very, very important. Okay, have we begun studying the weather patterns on the planet? Try to forecast them, like trying to predict. Okay, so this question is about, have we tried studying weather patterns on other planets and tried to forecast them? There actually is a satellite going to Mars, and I heard about this in a Mars 2020 talk. So it's not even my information, but I know that there is a satellite going to Mars that's essentially a Martian weather satellite, and they are going to try to understand Mars weather patterns better. And I wish I could remember the name, and I think the United Arab Emirates was involved in that particular mission that I'm thinking of. But I definitely know I do know that that's happening. So, oh wait. I've heard 5G frequencies might interfere with H2O frequencies and affect forecasting. Is there a general conflict between weather observation and uses of radio frequencies or other satellites trying to use similar orbits? The 5G problem is definitely an ongoing thing, especially with the ATMS microwave instrument, because its lowest band is close enough to the 5G channel that there would be significant interference between that and the ability to use that channel. And we can run tests to show what would happen if we lost that channel altogether, how much that would affect the accuracy of the forecast. But In truth, we're likely only to lose it over cities that have 5G. So major cities would see a reduction in their weather forecast accuracy, which is a problem. And there's different talk about solutions, but no solution has been reached yet publicly. And so it is definitely an ongoing problem, and it does affect microwave instruments the most, the 5G frequency. So let's see, I answered that. Okay, are there concerns from other countries that weather satellites could be used for spying? I'm sure there are concerns, but the fact that if they have specific broadcast information, if they have, we do this thing called direct broadcast. And so as the satellite is flying over, it is sharing all the data that it is collecting as it's flying over. And that kind of transparency, I think, alleviates most people's fears for spying, but there's an awful lot that you can see from a weather satellite. And I think most people understand the benefit of taking that data as opposed to leaving that blind spot. But I don't know of any specific concerns or people trying to shoot down weather satellites. Let's see. Can you talk about the future of weather control? Well, in some versions of this talk, I did have a few slides about controlling the weather, and I was taking it from a science fiction standpoint of, haha, what happens when we can control the weather, because we barely understand the weather, how can we control it? But apparently, we have tried to control the weather. With cloud seeding in particular, we can make it rain early, we can make it, well, with existing clouds, we can seed them and make them rain early. And this was used to control nuclear fallout from Chernobyl. They tried to make rain clouds rain before they hit Moscow, so the radioactive particles would fall on land that was not occupied. There was also, during the Vietnam War, they tried to increase the length of the monsoon season to wash out the Ho Chi Minh Trail. And this came out in something called the Pentagon Papers. And then there was this whole public outcry because, well, there was a public outcry because it was just cruel to mess with the weather like that. And now there's an international treaty that we will not use weather for warfare. It doesn't mean we won't continually try to control the weather, because they still do around airports to reduce fog. They still have some limited amounts of control. But there is an international treaty, and as long as the people who signed it obey it, it'll be fine. There is a problem, though, in terms of herbicide warfare, because killing an entire country's crops does not fall under that particular treaty. But it's still pretty cruel from a humanitarian standpoint. So there's always this balance of, as soon as we have the ability to control the weather, there might be an ability to use that for negative consequences around the world. But we're not good at it at all. Is the SpaceX Starlink fleet of concern to weather observations? I haven't heard that it is. In fact, from a programmatic standpoint, we are looking into how we can follow the model of small sat constellations and take advantage of global internet to get our data down to our forecasters even faster. So we are watching them with great interest to see how successful they are. But I haven't heard about concerns to weather observations, but maybe my ear is not close enough to the scientists that are crying out about that. Let's see. I saw one up here. Can you describe how wind speed and direction are detected? Are there photons involved? There are always photons involved. If you're talking about from a weather satellite, it would be, there's a lot of indirect information that we get from the motion of clouds. And if you've looked at pictures of the Earth at any given time, there are lots of clouds everywhere. And if you see a picture of the Earth that doesn't have clouds, chances are they took an awful lot of pictures, and they took an awful lot of pictures and they filtered out the clouds. And cloud filtering is actually a bigger deal. But without having seen the wind speed direction things, I do believe that understanding the motion, like the time difference, is a big deal. So it's easier to do with a geostationary satellite than a LEO satellite, because you have you have an image every 5 minutes and you can see how things might be moving and how clouds might be moving in that area. But in terms of what a weather satellite can do, if it doesn't come by photon, it doesn't come. So let's see. I can done these, and then it becomes easier to see what all your questions are. The problem is I plugged in a Windows mouse to a Mac and my scroll buttons are inverted. Okay. Let's see. With the increasingly widespread deployment of cheap terrestrial sensors, do you see any closer integration between sensing from satellites and sensing at ground level? There's already super close integration between sensing at satellites and sensing at ground level. There's a wonderful visualization at the Science Visualization Laboratory that shows all the sources of data. And actually, one of the sources is every airplane that flies across the US is sending down additional data to weather forecasters. And maybe it only makes up a small percentage of it, but the lack of flights that's happening now with the lockdown, or the decrease in flights, actually does affect our ability to forecast the weather. In terms of local forecasters, it depends on the local forecaster and the deployment of the sensors, but we always are trying to get more, we always want more data in certain spots. And then we also at the same time are suffering insane information overload. So, so I think it would depend on the individual forecaster and what they are able to put into their model and their computing power, and how they're able to integrate that data. Because I mean, if you look at the news when there's a snowstorm and somebody has a yardstick in the snow in their backyard and someone else has a yardstick in the snow in their backyard, even that kind of information can be helpful to a local forecaster, because it will show differences on a scale that you cannot see when you when you're just looking at a satellite that has 350 meter resolution. So let's see. I have a 2-minute warning here. So what I want to say right now, oh, there's one last question. As weather satellites age and get replaced, are they replaced at a rate you feel is sufficient to sustain your data analysis? I would say there's definitely a lag, and there's quite often a risk of data gaps in terms of that. And we managed to find a way, but I know sometimes there are just unavoidable data gaps in that. And so that's a good question. But as I am out of time here, I'm going to head over to the Discord, the Science-Skeptics After Panel Conversation. And you guys can continue to quiz me there. And thank you all for coming. And I very much appreciate it. Again, my name is Valerie Mikles, and let's see. You can find me online. I'm Valerie Bean or ValerieJMikles.com. And I believe in the chat, there's been a link to the Discord. So Thank you, everybody. And I appreciate you coming. And I will see you in Discord.